So, as she mentioned, I'll be talking about an introduction to functional programming, where you should learn about what the core of functional programming is, how it can help with problems you've already encountered and in projects you're already working on or will. That it's not necessarily hard and complicated, and that although neckbeards are welcome, they are not required. I don't have one, and I'm speaking about it, so you'll be okay without one. And we'll cover what makes a functional programming language, what do you need to do functional programming in a language, what's immutability, what's putting off side effects, what's referential transparency, some common traps when talking about it with other people, and where you can go to learn some more. And it all, to me, comes back to stopping things from changing behind my back and making everything very explicit. So we can stop things, except for these slides, from changing behind my back. So what do we need in a language to do functional programming? So the main thing we need is first-class functions. So functions can be objects. So you can pass functions into other functions, and functions can return functions as a result. And there's a lot of other things that are really, really helpful and make it much, much easier and much nicer, which is available in a lot of languages that aren't necessarily considered functional. In this talk, I'll be using Python to demonstrate the examples, which has some of these things. And you don't, even if you're not using a so-called functional language, you can adopt a lot of these practices. I'm a Ruby developer, which is definitely not considered a functional language, but I still use mutation rarely enough that it attracts comment if I do. So we'll start with immutability, which is when you, instead of changing your values as variables, you can create new ones that have the values that you want. So you would use recursion and accumulators over loops and mutation. And just to check, how many of you are familiar with recursion? Cool, that's good. And if you've ever felt confused about whether you're passing by value or by reference because you're worried that something's going to change it, if you're not mutating, then nothing bad's going to happen because it's not changing. And sometimes mutation in code, particularly when it's got a really wide scope, can lead to some really confusing problems. There was one case when I was working on this build file. We had to add a new custom task for some custom contract testing things so we could check what came in and out of different services. And we added our new task. We had to add this special dependency. We had to filter the list of dependencies down to the one we wanted to use, and then do a thing to it and run our tests, which we did, and it worked, and it was wonderful. So we went to run the whole suite of tests, going, oh, we only changed this one thing. We added something. We didn't even change anything that was there. Of course it's going to work. We'll just check before we check it in to be sure. And everything was completely broken. So it had all these problems with not being able to find a single one of the dependencies. Because it turned out that in Groovy, which these build files were written in, if you filter a list, it, as well as returning the filtered list, it changes the existing list to be the filtered list. So we'd gone and deleted every single build dependency other than our one. So absolutely everything else was completely broken. And I've got some examples to help demonstrate this. So we'll be working with items in a shopping cart. So how many of you have touched Python before? Oh, cool, that's far more than I expected. That'll make it easier. So this is a class item, which just has a cost attribute. A real one would have more stuff, but that's all we need for the examples. And the init method is called when you create the object, and then there's just some other stuff so we can compare it that we don't really need to go into. It just means we can check if things are equal. So say we want to add GST to these items. So we have this function that adds in the GST. So note that it creates a new item and it gives it the old item's cost multiplied with the GST multiplier. So instead of modifying the existing item, it's creating a new one and returning the result. So we're not mutating the one that we receive. And we also use recursion and accumulators over loops and mutations. So this is an explicitly recursive solution, which is just easier to get an idea of how to approach these. So we're splitting our list of items into a head, the first element, and a tail, which everything else in the list goes to. And if we're up to our last element, so the tail is empty, then we do our base case, where we just call with GST and chuck it in a list. Otherwise, if there are more elements, we'll do the same thing, except we also get the function to recursively call itself, and we add those two lists together. But this approach is quite verbose, so there are some other ways to do this, which is quite a bit shorter and has less of the boilerplate, because you do the same dissecting the list over and over and over again. So that can be taken out. So in Python, you'd often use a list comprehension to do this. This does the same thing as the previous slide. So it goes through each item and runs with GST on it. And in a lot of other languages, it'll tend to be done differently with higher order functions. This is just different syntax for the exact same thing. Again, it still runs with GST on each item in items. You may have also seen this as collect in Ruby, but it's usually called map. And say we want to total up the cart, so we are collapsing a whole bunch of values into one. So this is different from just modifying each item in the list, we're collapsing it together. So we could do a non-functional mutable solution where we make a total, we loop through all the items, and we add the cost onto the total and return that. And that's the mutable solution, or we can do the other approaches. So the explicitly recursive solution is actually even more verbose than the mutable solution, but it's often a nice midpoint when you're figuring out how to do it in a more concise way. So this looks pretty much the same as the previous one, which is why we abstracted out. You're dissecting the list into head and tail, and you have your base case, and then you have your cost plus recursive call. Sorry. And we can also do it in a tail call recursive way. Now, this approach isn't useful in Python, but in other languages, this can be optimized to use a lot less memory than recursive calls was on the stack. We'll get to more on that later. But the key difference is that at the end of the function, the last call is a call to the same function again, which allows it to be optimized. So we have an accumulator, the total, which is passed through each call. And the base case will be the total, the accumulator, plus the cost of that last item. And we pass that right down. Or we can also use reduce, which is a far more concise way to do it. You may have also seen that called fold or inject. So this one does exactly the same thing as the previous ones, just in a slightly different way. So you make a lambda, which takes a total, the accumulator, which goes first, and the current item, and it adds them together like we did in the previous examples. And you have to give it the list that it's operating on, and the 0 is just the starting value for the accumulator. So that's equivalent to the total equals 0 in this previous one. And now we'll move on to side effects. So side effects are whenever your code does something that affects the outside world. So maybe you're printing something, you're writing to disk, you're doing some network calls. It's what your software does. And it's really the reason that you're writing it. And in functional programming, we separate the logic from those side effects, and we push the side effects out to the edge. And the middle of the system makes a representation of what we want to do, and then we actually do the side effects at the edge, which makes the core easier to test and reason about. It becomes just inputs and outputs, so it's really easy to see what's going on. This also makes the testing in the middle easier, because testing the side effects is far more difficult. And contrary to what some people believe, it's not about getting rid of the side effects, otherwise your software doesn't really do much. but you need to control them and make them more explicit so you can reason about them. So if we want to print out the result of our add.gst thingo, a non-functional approach to it, which is quite simple to implement but not so to test, we would just put in writing output right in the add.gst function, and it looks straightforward at this stage and it works. We have to inject in the stuff to write it out so we can test it later. Or if we want to take a functional approach, we can create a function that has the sole responsibility of doing the output. So we separate out the two responsibilities of doing the calculation and doing the output. And then we feed the result of one into the other. So we've separated the responsibilities. And the difference becomes much clearer when we go to test it. So when we go to test just the calculation part of the one that has printing right in the function, we have to mess around with making our own string IO and injecting it. And the test intention isn't super clear. We have to process the string a bit to get what we want out of it. And the intention of the test isn't as clear as it could be. But if we go to test the calculation in the functional approach, then we're just looking at inputs and outputs, and the test is really simple and the intention is really clear that that's the result that we should get when we're adding GST, rather than having all the other stuff going on, which gets more complicated in real systems. And we get referential transparency when we combine these. So it means that when we call a function again, we'll always get the same result, and there'll be no side effects going on. And that means we can substitute the saved result for a function call, and that everything that the function does is expressed in the result. So we can just look at the result and we know everything that's going on. So if we have something that's referentially transparent, we can have the same line of code in just about the same place and it does exactly the same thing, which seems reasonable. So these two lines are the same and do the same thing, which makes sense. But if our code is not referentially transparent, for example, this one mutates, then we do the same thing in just about the same place and we get different results. In this example, it's a bit clearer, but we can end up with the more problematic examples like deleting all the build dependencies that I did. Or worse, you could have subtle bugs that you don't pick up as soon as you run it, but cause weird problems that are really hard to track down because the actual problem is probably a long way away from where the bug is manifesting itself. And when talking about functional programming and using Python, tail call optimization is a bit of an elephant in the room. So when you do recursion in Python, for every call, it puts another frame on the stack, so it uses a whole lot of memory, and it's quite inefficient, and it doesn't look like we're ever going to get tail call optimization in Python, but it is available in a lot of other languages. But to get around this, we can use the higher order functions or list comprehensions, because they still do really the same thing from how we can reason about it. And it's also much more concise. You don't have as much boilerplate. It's much more readable once you have your eye in, because you can really just jump to the bit that's actually doing things rather than the boilerplate. So you can get around that quite easily. And there's also something called trampolines available, where you put your recursive function inside a wrapper that converts it into some go-tos, but I don't think that's very nice, but you can look at it if you would prefer. And some people claim that functional programming clashes quite a bit with OO, and you're quite likely to end up working in an environment where you're doing that because it's very popular. But in my opinion, it really doesn't, because they say that mutation of state is really fundamental to OO, but I don't see how making objects that have the value you want instead of changing existing objects has anything to do with it, really. I don't see how that affects that. And some practices that people really into object orientation like to talk about, like separating your commands and your queries, actually fall quite well into separating side effects. But this is, and if you want to go to teach some of this or get people in your team interested in it, something that I see people, that I'm also prone to, that people do a lot, is getting really mathematical when explaining functional programming and turning off people that don't feel that they're good at maths. They may actually be good at it, but if they don't feel that they are, they can get quite turned off by that. And it can be helpful to relate it to things they already know. So I've had great success not actually using the technical terms until after people understand it, particularly when they're intimidating technical terms like monad, when explaining to people that have actually already used it a lot. And you need to make a big effort to fight the really academic and impractical image, because that's pretty hard to break out of, and explain that you can use it in the real world for real working software. But this is super introductory, so if you want to get into it, you should go and learn more. So I've got quite a few Python resources, so it's good that lots of you have some experience with that. So there's an introduction in the Python docs, which has some really good examples, but I disagree with some of the details. It advocates for local mutation, which just seems a bit odd when it's unnecessary. And they claim that OO and functional programming clash, which I mentioned before. And all of my, there'll be a link to my slides at the end, so don't worry if you don't catch it. You can just look at it on GitHub. There's a whole series about functional programming in Python here. There's a tail call optimization trampoline implementation, which I don't think is very nice, but if you're keen to do that, there it is. An introduction to using some of those higher order functions, which is the approach I'd recommend for working with collections in Python, and it's also good in other languages. And they work pretty much the same in other languages. The arguments might be in a different order, but it's conceptually the same thing. Dive into Python's got a chapter on it. And there's some really good exercises in the Python practice book, which are much more approachable than most of the other exercises I've seen. And there's a book about it, which I was intending to check out before I gave this talk, but I didn't get around to it. So I'm not sure how good it is, but it's a thing. And there are also a lot of non-Python resources, which might be less approachable, but they'll often be more in-depth. I really liked doing this course when I got started. So I first did functional programming when I joined a team that was doing Scala at REA, and they got me to do this for my first week, and it really helped. I started to have a clue what was going on, so that was great. And if you prefer books, that book's quite good, but it can get a bit dry. If you came into this wanting to find out what a monad is, I didn't have a long enough time slot to include a monad tutorial, but that is a really good talk about it. He goes and does a whole lot of refactorings with monads and then explains that they were actually monads all along at the end, and I think it's by far the most approachable one, because a lot of them are very unapproachable. A lot of them don't make sense even when you know what they are. Yeah, check out that one. It's so much easier to understand. Even if you don't know Ruby, it's easy to read, and it's far easier to understand than most of them. Go to that one. Some practical exercises in Scala are available here. That should probably be done in supplementation with one of the courses or books, because it doesn't have much explanation in it. I've done it guided, but you'd want to have something to supplement it. And there's also a NICTA course in Haskell, which is probably the same, have other materials to supplement it, because apparently on its own it's a bit of getting thrown into the deep end. And as we discussed, like avoiding the mutation, avoiding the side effect, it really comes back to stopping things from changing that we don't know about and making it easier to reason about what's going on in our software. And do we have any, you can get the slides at that link or follow up to my email address. And are there any questions? Yep. So the argument I've heard before was that mutation is important to object-oriented programming, but I don't see how that is. I don't see how making a new object clashes with it. And say in some of the Scala stuff I've done at REA, we were fusing functional and object orientation, and that seems to work, and I didn't see them clashing at all. And the person who was referring to test-driven damage, he did end up backing off quite a bit when he came to actually discuss it. I think he was trying to be controversial and get attention, which he definitely did. He backed off a bit, but it sounded... That was several years ago. From what I remember, he maybe wasn't doing TDD that well, and maybe it wasn't necessarily suited to what he was doing all the time, rather than he's thinking it's problematic all the time. I think he meant some of the time, but he came out a bit strong. So while you're doing object-oriented programming, you'd also make your objects immutable, and you would separate out your side effects. So similar to how you would apply the principles while still doing object orientation. Any other questions?